So veins are blood vessels that return blood to the heart. And because they are kind of at the end of the circulation, the blood pressure there is very low. And this is a challenge that veins have to overcome, being able to return blood to the heart despite a lack of blood pressure, right? So imagine, you have like some sort of, like circle, and you are trying to kick a ball around the circle back to yourself, right? When you kick the soccer ball, it's going to be going really fast right away, but as it comes around the circle, if you don't kick it very hard, it's going to struggle to get back to you. Same idea with blood, right? Getting pumped from the left ventricle and out into the systemic circuit, whoosh, right? And it's going really fast with a lot of pressure. And by the time it gets back, it's just trickling back into the heart, right? So how do we improve blood return through the veins with this lack of pressure? Well, one way we do it is with valves. Valves are one way, and they prevent backflow. So blood can push through them pretty easily, but if you try to push blood back up the other way, they don't budge, right? And so this allows you to essentially like save your level, right? If you're playing a video game that's very, very hard, you may want to sort of save your level, and that way, even if you, get your character killed a bunch of times, you're still going to be able to start again back where you have made it. And keeping blood moving is important, as we talked about in the last chapter, or the blood chapter, I should say. If your blood isn't moving, it can clot. It's more likely to develop clots because prothrombin can spontaneously convert to thrombin. And also because you can end up with blood pooling in veins, and it can get pushed outwards and distend those veins. And that can happen especially in places where your valves maybe aren't working properly and you have a lot of pressure pushing on that blood. So when you have this distended veins, we call these varicose veins. And you tend to see those, often in people's legs, for instance. But you can also have varicose veins in the anal canal, and we call those hemorrhoids, right? And again, in times where you have a lot of pressure down there, if you're pushing exceptionally hard, or if you're having a baby, right? People often get hemorrhoids after childbirth. You can get varicose veins in that anal canal. In addition to valves, which help prevent backflow in your veins and so help you improve venous return of blood, you also have some other ways to increase your blood pressure. So one is your skeletal muscle pump. And your skeletal muscles, whenever you use them, they squeeze, right? That's what contraction is. And when they squeeze, they create pressure and they shoot blood up, right? They would shoot it back too, but your valves prevent this backflow. So they just shoot it forward. And so every time you move your muscles, you are improving your venous blood return. And this is another reason why exercise is really, really important for your circulation. So this is your skeletal muscle pump improving venous blood return. You also have what's called a respiratory pump. When you breathe in, that squeezes in on some of your veins too, and just like your skeletal muscle pump, causes blood to get squeezed back towards your heart. Some of your veins are even right next to arteries, and arteries are constantly getting larger and smaller with the systole and diastole of your heart, of your ventricles. And that change in size pushes a little bit on the veins. And even then, that can create a little bit of pressure in your veins to push blood towards your heart. Now, because blood is moving so slowly through your veins, because of that lack of pressure, and also because a lot of your blood moving through veins is going from your intestines to your liver for processing, and then it spends some time in your liver, getting detoxifying harmful molecules and adding blood proteins and things like that. Most of your blood at any given time is in your venous system. So in the veins of your systemic circuit is 64% of your blood on average at any given time, as opposed to your systemic arterial system or pulmonary circuit or a heart. And while your veins don't have to deal with nearly as much in the way of pressure shifts as your arteries do, they still have smooth muscle fibers in the tunica media. And one reason for that is to allow them to maintain blood pressure, even if your blood volume drops. So even if you have some blood loss, you can cause your veins to get smaller in diameter. And just like putting your finger on the end of your hose, right? If you have the same amount of blood but less volume, the pressure is able to go up. This also allows you to route your blood through either superficial or deep veins, right? If you make the superficial veins narrow and the deep veins wide, more of the blood's going to go into the deep veins. And you do that, for instance, when you're cold. You want to keep your blood near your core. When you're hot, you do the opposite. You make your deep veins narrow and your superficial veins wide, and you send blood to your surface, and that allows you to cool off that blood when you need to. And here's an example of what happens when you have some sympathetic nervous stimulation of those veins. You can see how the diameter has gotten smaller. It's narrower because of that smooth muscle contraction. And again, this would happen if you needed to up your blood pressure all of the sudden, right? If you were being chased by a lion and you had to get blood fast to your muscles, you would up your body's blood pressure by constricting your veins. So in the last chapter, when we talked about the heart, we mentioned how you can regulate your cardiovascular system, your blood flow, by regulating your cardiac output, right? If you increase your cardiac output by either increasing your heart rate or increasing the stroke volume, then you can crank out more blood pressure and push blood through all of those vessels that you need to push it through. But you can also regulate blood flow, as we were just talking about, using your blood vessels within your systemic and pulmonary circuits. And whether you're using your heart rate or your smooth muscles in your blood vessels to regulate your blood flow and blood pressure, you can have autoregulation, which means some local action, or central regulation, which means neurons from the brain and hormones. Autoregulation is a local action. Central regulation sends things to central command. So let's talk for a few minutes about kind of the physics of blood flow, of fluid movement. Fluid moves from an area of high pressure to an area of low pressure, right? That's why when your ventricles contract and make a lot of high pressure in your ventricle, then it pushes out to the vessels where there's lower pressure. And if the pressure is higher in your ventricles than in your vessels, the blood will flow towards your vessels. When you create this pressure, this blood pressure, meaning the pushing of blood on the walls of your circulatory system by pumping blood. And the pressure begins to meet greater resistance as you get into smaller and smaller vessels. And resistance is going to be a force that opposes the movement of the blood. In this case, it's peripheral resistance that comes from the vessels, right? So as you are moving through the vessels, the blood on the sides kind of gets slowed down by its contact with the vessels. So imagine you're walking through a hallway with a bunch of people. The people on the side kind of keep getting, if it's a crowded hallway, pushed up against the wall, and the wall, slows them down, right? Kind of pushes back on their movement. People in the middle, not so much. But if you have a wide hallway, right, very few people have to be on the edge being pushed against the wall. If you have a narrow hallway, a lot of people do. And so we'll talk in a moment about how this peripheral resistance works. But it gets higher, this peripheral resistance, as the vessels get narrower. And so your capillaries, which are by far your smallest, narrowest blood vessels, have very high resistance and so very low flow, right? Your pressure meets your high resistance, and then flow is slowed down. And this is good because this allows time for exchange of gases and wastes and nutrients between your blood and the interstitial fluid. And then by the time you get to your veins, you maintain some pressure because of valves and the skeletal muscle pump, muscular compression, and your respiratory pump. And then the veins get larger and larger and larger, which means less resistance. So even though the pressure is lower, the resistance is much lower, and so you still have flow. So let's dig in more on peripheral resistance. There are really three factors that involve: vascular resistance, viscosity, and turbulence. And vascular resistance, as we were talking about, has to do with how much of the blood is pushed up on the side and rubbing up against the walls, right, which slows the blood down, and for how long that happens. And so length and diameter of vessels really matter. If you have a longer vessel, right, your blood has been, some of it at least, pushing up against the side of the walls and being slowed down through friction for a much longer time, and this is going to, over time, create an accumulated large resistance. So imagine that you are drinking through a straw, right? Now imagine that the straw, you put like 30 straws together and then put your Coke on the other side of the room, and then you tried to suck through the straw, right? It's going to be a lot harder to suck that fluid through the straw when it's 30 straws long across the room rather than a very, very short one, right? So the longer the vessel, the higher the resistance. And as I mentioned earlier, diameter also matters, right? So if you ever go to Burger King and you order Pepsi, because they don't have Coke, unfortunately, you order a small Pepsi and it shows up and it's like a bucket, right? Their smalls are enormous, and you think, I'm never going to be able to drink this much Pepsi. And then they give you your straw, and your straw is huge. And then you put it in there and you start drinking, and in no time you're finished with that gallon of Pepsi. Now it moves faster because, for whatever reason, at Burger King they give you giant, thick straws, right? There's less vascular resistance because of that. And this is because there's always the greatest flow at the center and the least on the edge where you're sort of rubbing up against that wall. And so in a greater diameter straw or blood vessel, a smaller percentage of the blood has to touch the walls, whereas in a narrow vessel, a greater percentage of the blood has to touch the walls, and so you get greater resistance. So a short, wide vessel has very little resistance. A narrow, long vessel has very high resistance. Again, imagine you're drinking something through a straw, and that can help give you an idea of this resistance. All right. In addition to vascular resistance, your peripheral resistance can be affected by the viscosity of your blood. Viscosity is sort of the thickness, the resistance to flow. So water has a very low viscosity. It moves quickly. It flows well. Molasses has a very high viscosity, right? If people tell you you're slower than molasses in the wintertime, that's because if you try to pour molasses or, very thick syrup, onto your pancakes, it's going to take a long time to flow. And your blood is about 5 times as viscous as water. And becomes viscous because of all the stuff in it, right? Your blood is largely water, but it's water with cells in it and proteins and sugars and amino acids and all those things. And the more stuff that's in it, the more viscous it is. So now imagine you go to Wendy's. I'm on a fast food kick here, but you go to Wendy's and they give you a Frosty and they give you a straw and you're in your car. So you can't just bust out a spoon, right? You got to drink it out of the straw. You can't. Right? It's not a normal milkshake. A Wendy's Frosty is really viscous. And so you expend all of your energy trying to get just a little taste of that Frosty through the straw to your mouth. And it's very difficult because of viscosity. So now imagine, a really long, narrow straw, like a coffee stirrer, put into a Wendy's Frosty, right? You're never going to be able to get that stuff to you because there's a lot of peripheral resistance because of the length and the diameter, and there's a lot of viscosity. Now, your viscosity of your blood can be affected when you, for instance, add more proteins or more blood cells. This is one reason why blood doping, like they do in cycling sometimes illegally, is bad for you because it increases your blood cells, also increases the viscosity of your blood, and that can be dangerous. And this is a figure from your book that gives you a general idea of sort of the relative viscosity of a number of substances. The last thing that can influence resistance is turbulence. And turbulence you think of in a plane, but it's anything that disturbs the flow, right? If you have straight line flow of water or air, it moves relatively easy, low resistance. But let's say you have a stream and you put some rocks in it. Then you hit those rocks and you get swirls and eddies, and all of a sudden there's more resistance to flow. That's what's happening in the air too. It's causing you to bounce up and down. It's disturbances in the flow of air, and that makes it harder to move the air or the water, or in this case, your blood. It creates resistance. Now, plaque deposits can do this in your blood vessels, right? They create this turbulence in the flow. And again, turbulence, viscosity, and vascular resistance due to length and diameter can all cause your blood to slow down.